Hi, my name is Elbaum Stein, and this is a brief introduction to DeepManeuver, my technique for adversarial test generation for the trajectory manipulation of autonomous vehicles. So fundamentally, adversarial testing is about robustness. Why, as software engineers, do we care about the robustness of autonomous vehicles? First and foremost, the answer is safety. 3 flagship AV systems have had high-profile crashes that involved a failure of the neural networks to accurately interpret the driving environment. And this is not unique to these systems. Our community has documented many instances of failures in AV software. 2, AVs are expensive. The hardware alone represents significant costs. GM Cruise was using 5 separate LiDAR sensors and still did not produce a regulation-compliant vehicle. Finally, AVs are multiplying, with the AV market projected to reach a valuation of $600 billion in the next 8 years, with 20% of that coming from the deep learning subsector. Now, what is it about these systems that makes testing so difficult? Well, the tasks involved in successful autonomous driving are complex, not just sensing aspects of the driving environment, but trajectory prediction for itself and other traffic vehicles. The AV must then actuate those tasks, many of which are safety critical. Moreover, the input space for a single sensor onboard the AV is large, and the input space for all sensors is combinatorially larger. Most of that space is noise, and constructing semantically meaningful images has proven difficult for even the most sophisticated diffusion models. Furthermore, the long tail of driving scenarios ensures we cannot test the input space exhaustively, only strategically. With the growing prevalence of AVs, these rare events in the long tail occur more and more frequently, and the long tail of driving scenarios is ultimately what drives the case for adversarial testing of autonomous vehicles. Adversarial perturbations like these can give you a measure of the local robustness of the onboard neural networks relative to the input set used to derive the perturbation, but they do not always result in system-level consequences like crashes or misbehaviors. On the following slides, I'll show you an example of what I mean. Deep Billboard, for example, calculates a patch attack from a set of static images. The patch is optimized well for these images, which are all taken from standard driving. In this image, the blue shaded area shows the part of the track where Deep Billboard collected the images used to generate the perturbation. As you can see, as the car state, position and orientation, drifts in and out of this blue area, the images drift out of distribution for those for which the perturbation was optimized. This leads to a reduction in perturbation strength and minimal change to the actual driving behavior of the car when the perturbation is deployed under test. Compare this to our technique DeepManeuver, which takes the compounding effects of the perturbation into account and is able to enact system-level failures like crashes more consistently. This is the high-level perturbation generation loop for DeepManeuver. It iterates between simulating the effects of the perturbation and optimizing the perturbation for new images from the simulator. The perturb function optimizes for 2 different losses, L-previous and L-current. L-prev preserves steering perturbations accomplished in previous time steps, upon which the current state of the vehicle is dependent. And L-cur optimizes the perturbation for the current image, which determines steering for the upcoming time step. So, at this initial stage, L-prev is nothing, and L-cur is optimizing the perturbation for the current image, weighted by the size of the billboard in the image, which is a function of distance. As the vehicle advances and the perturbation is optimized for more and more states, the compounding effects of the perturbation are taken into account as the vehicle drifts out of phase with safe driving. So we have a perturbation, this patch at the bottom left of the slide, that is refined to fit the distribution shift. For more details, I encourage you to check out our TSE paper. As a result, the vehicle crashes at a far more consistent rate under test runs using our DeepManeuver technique to generate this patch. Our study compares Deep Billboard and DeepManeuver, our technique, for affecting system-level performance metrics as well as DNN-level accuracy metrics in a variety of driving topologies. This is one example topology that corresponds to the running example in this presentation. It shows the approximate average case, which is about 20% Deep Billboard tests resulting in a crash, versus almost 50% crashing for DeepManeuver. I again encourage you to refer to the TSE paper and its appendix to learn about the different road topologies and perturbation configurations that we studied. The other bonus of state-adaptive perturbations is you can change the effect of the perturbation based on the state of the vehicle. So here the car is made to drive towards a specific waypoint in order to cut the corner, a racing tactic, rather than drive in the center of the road, which is the standard driving behavior for which the DNN was designed. In conclusion, adversarial perturbations can be self-defeating due to input and state distribution drift, and current applications of adversarial attacks don't consider state, and they need to in order to account for compounding effects of an adversarial perturbation. The DeepManeuver technique is open source and available via GitHub, and I'm always happy to chat more about adversarial attacks. Thank you so much for your attention.